and let's get started with them. Our first speaker is Pascal Chabert, and he will talk about plasma thrusters, a fascinating playground for the low temperature plasma scientists. Pascal, please go ahead.
Okay, thank you, Shahid, and thanks for the committee for this invitation to speak. I'm working at the Ecole Polytechnique in France, and I've been working mostly on plasmas for etching in microelectronics, but now I'm working a little bit with thrusters. So the motivation for this talk is that our community has been historically driven by industry, from lighting, gas lasers, to metal processing, to microelectronics. But recently, enthusiasm has moved towards new appealing, but not necessarily yet industrial applications, like, for example, cancer treatment or agriculture. Plasma thrusters, in fact, were mostly in the new appealing application category for a long time, but now they have become the main and maybe soon the only engines for newly launched satellites. And therefore, they sort of move in the category of, like in microelectronics, of working devices, basically. And basic plasma physics, like concern about instabilities, anomalous transport, turbulent transport, waves, all this was a central piece of the research carried out in thrusters. However, new designs and new propellant that will be used now, like molecular gases propellants, make the thing that such topics like plasma surface interactions, plasma chemistry, negative ions, or all kind of low temperature plasma community subjects are going to be investigated. Therefore, that's why I wanted to draw your attention on this, because I believe the plasma thrusters offer actually a fascinating playground for low temperature plasma scientists at large. A side effect of preparing this talk is that I realized that quite often, if you want to motivate good students, raise research funds, or even reinvigorate your own interest for research and motivation, you seem to need something new and promising that requires scientific breakthrough. So what is new and promising? I realized that it's essentially something that does not work. It's easy to motivate your research when it doesn't work, because then you will have to make it work. And something unexplored, something with high social impact, with sort of the save the world flavor is maybe desired. But then I realized that in my own experience, I didn't do this at all. In fact, I worked only on not new and not promising areas. I worked in plasma etching for microelectronics. I worked for plasma thrusters now, and all this is working. So you would think that you're not going to do any interesting research in this area. But in fact, over the years, I've seen significant research progress, even maybe breakthrough in the fundamental aspects of low temperature plasmas, and this was done in plasma processing and in plasma thrusters. So I came with this somewhat counterintuitive conclusion. It is not only possible, but even maybe necessary, and a good thrust to fundamental research is to work on working applications. So why space? In fact, space is a growing area, clearly. You see the investment of government in space is growing up quite fast. And in fact, it's also the case of private sector now. You have a very large amount of satellites in orbit. And of course, we all know about telecommunications and GPS, but there is also Earth observation, which is already and is going to become very, very important. So I have actually stolen those slides from Thomas Charwa, who just submitted his thesis, and he had this nice video about how we monitor any type of climate change using satellites, and this is of course a key issue for humanity. So space is clearly very much needed. If you want to be in space, you need some engine, you need some space propulsion, because you need station keeping, you need to maintain your satellite in orbit, you need also to change your orbit of your satellite. You need to remove debris, a very important aspect. And also, since scientists, we're also concerned about exploration, and deep space exploration needs, of course, engines for propulsion. Plasmas, why are they useful? We all know that, but I just refresh your memory. Because you can access very high exhaust-velocity of the propellant, because you accelerate the particles. You get to what people call the specific impulse, a very high specific impulse, and therefore what you can do is pretty much have low thrust engines, but engines that are very efficient in terms of propellant consumption. So if you launch a satellite with a chemical engine, you will have 2/3 of the mass that is in fact propellant. Whereas if you launch a satellite with a plasma engine, then only 15 to 20, between 10 and 20% of the mass is propellant. So that's why it's extremely interesting. Recently, as I said, it has become even more exciting because, in fact, it used to be until very recently, maybe 5 years ago, that a satellite was equipped sometimes with plasma thrusters, but almost always with a chemical engine, and mostly for orbit transfer, for example. Now, even the GEO satellites and even the big satellites are fully equipped or will be entirely equipped with plasma thrusters. So it makes a whole new market, because you will have to have high power thrusters, even for commercial applications and to put telecom satellites in orbit in GEO. And at the same time, you also have an all new enthusiasm about low orbits, where you have smaller satellites, even down to very small size, like CubeSats, like 10 by 10 cube, so very small satellites, and those also will need engines. So you started with a station keeping thruster that was pretty much about 1 kilowatt of engine, and we need now to go to 5 to 10 kilowatt to do orbit transfer, and we need to go down to 1 to 100 watts to do small sats, and therefore you have a huge new market open, and therefore research needed to do this. So in this talk, just to show you that plasma thrusters are not only turbulent or anomalous transport or kinetic theory, I'd like to show you some aspects of research that is extremely important. And I will use two vehicles. The first one is going to be the Hall thruster. Hall thrusters are the most famous, the most studied, and probably the most used now in space thrusters. And I will also speak about ion-graded thrusters more in the sense of what we could do maybe new, or what kind of innovation we could do in thrusters by using other concepts. So Hall thrusters. What I'm going to show you is that it's very complex, but that actually some physics that we do routinely in low-temperature plasma physics, like the sheath physics, for example, is absolutely important. So a Hall thruster, it works like this. It's a very complex device. In fact, you have a cathode that emits electrons. You have an anode on the other side. So there is an electric field that points in that direction towards space, towards outside here. And this electric field is going to accelerate ions out, and this is what is going to produce the thrust. The electrons emitted from the cathode will both go back to the channel, but also will be used to neutralize the ion flux outside the thruster. If you did not have any magnetic field, it would not run, because it's so diluted media, so low pressure, that the mean free path for ionization is typically 10 meters or even more. So you would not be able to break down the gas. So what you do is very clever type of design. You put a radial magnetic field here, which can trap the electrons. But not only it traps the electrons, but because of this electric field, you have an E cross B configuration that generates a very large azimuthal drift in that direction here. And therefore now you see that the mean free path for ionization is going to be very long yet, but still in the axial direction is going to be short, and therefore you will provide ionization. This device is in fact full of extremely complex physics. And first, you have some gas dynamics that is very important. I will not talk about this. But second, people have discovered very quickly that you cannot explain the mobility of electrons in this channel without going to very sophisticated instability-driven type of transport, anomalous transport, and it's been the subject of huge research. And this was carried out mostly by people with a strong background in plasma physics. In fact, people maybe at the interface with fusion science or space science, where all those phenomena are extremely important. But what people also discovered is that if you change the whole material here, if you move from one dielectric to another, if you change a little bit the composition of the material, then you find that you change drastically the way the engine works. And in fact, plasma surface interaction and sheath physics here has been quickly identified as a very important aspect. And therefore, I'm going to talk just a little bit about this to give you a flavor. Before I do so, just to illustrate complexity, I did one simulation from our group. Oh, I'm sorry, the video doesn't seem to work. Cannot launch video at the moment. Okay. Anyway, I will do it without video. This is in this slide. What I wanted to show you is different things. First, I'm going to take only the Z direction, the acceleration direction, and the theta direction where you have the drift here. So in this Z theta direction, we and other groups actually did particle in cell simulations to study the thing. And what was found is the following. First, you can see it on the figures, but let me describe this. You will find a strong localization of the electron temperature, a strong localization of the acceleration EZ electric field and ionization profile. And this is all due to the magnetic barrier that is here. So the electron temperature, to give you an idea, can go up to 20 eV or even higher, so higher than a usual low temperature plasma device. What you find also, and this was meant to be displayed in this graph, you see oscillation of the discharge current and on the neutral dynamics, and this is a low frequency oscillation due to gas depletion, basically. And in the azimuthal direction here, if you look at the electrical field in the azimuthal direction, you find that it's extremely unstable with a lot of fluctuations. And the fluctuations are typically with wavelength of the order of the millimeter and frequencies of the order of the megahertz. Those instabilities are responsible for anomalous transport. But what has been shown recently by many groups is that it's in fact even much more complicated than that. You don't have only one instability, you have several types of instabilities. Maybe you have wave mixing between all these instabilities. Maybe you have inverse cascade of the energy, turbulent transport. And all this is really a fantastic playground for research on basic plasma physics. Once again, maybe closer to fusion or to space science than to our usual low temperature plasma physics, let's say, playground. Now, what was done as well, again by our group, but again by other groups in the world, is to do simulation not in the Z theta plane, but in the R theta plane. R being this direction here, where you now going to account for walls, and theta again the azimuthal direction. And when you do this is the simulation. This is the R theta plane. So in R you have the wall here, and therefore you will form sheath, and you can study in detail what's going on in the interaction of this plasma with the sheath, the plasma being unstable in many cases. What was discovered very quickly is that because the electron temperature is quite high, in fact, secondary electron emission, not necessarily driven by ions, as it is quite often the case in capacitive discharges, for example, in microelectronics, but driven by electrons. In fact, electrons bombarding the walls and emitting another electron is going to be a very strong mechanism, once again, because electrons are quite hot in this annular ring of plasma here. You have many ways to model this, etc. There is a simple model that is like this, where you can see that pretty much you have a sort of a parameter here, epsilon star, which is a sort of threshold for emission, where the threshold where the emission is even larger than 1, and you can do you can use this model to study this in particle in cell simulation, but also in theory. And what people found in particle in cell simulation is the following: if the emissivity of the wall is not too large, being that this epsilon star is very large, then you're in a situation where the sheath is in fact first stable, but second looks very much like a floating sheath that we all familiar with a relationship between the floating potential and the temperature of the order of a few TE. If you now go to a very largely emissive material where the epsilon star goes very, very low, you end up with a situation where the emissivity is so large and the sheath potential collapses so down that you can even form an inverse potential in front of the electrode, which is going to enter a sort of saturated child law regime that is been known quite well. If you in between those two regimes, in fact, people found, we found, but it was studied quite deeply by the group in Princeton with see these references, for example. People found oscillation of the sheath. And I recently got interested in this and look into this, and I found a sort of a simple explanation, I believe, of this instability. But the reason I mentioned that now is that you need two ingredients in fact to see this instability. In this instability, what you need, of course, is emission from the surface. I told you that about a minute ago. But what we discovered as well is that we also needed an ingredient that is usually not included in the usual sheath physics, which is the fact that the electron temperature is in fact not constant in the sheath. Isothermal sheath approximation is not a good approximation. And the reason for this is because as you move toward the electrodes, the high energy electrons are captured by the electrode basically, and therefore you deplete the high energy tail of electrons, and the effective electron temperature that you observe is in fact lower than the electron temperature than the isothermal temperature that you would normally use. If you stick these two ingredients in a simple power balance model and sheath physics model, I don't have time to give the details, but if you stick those two elements, you find that there is a possible instability. Why? Because clearly, simply, the floating potential to bulk temperature relationship, which used to be, in a classical sheath, it's 5 CE, so you would have a straight line with a slope of minus 5 here. When you have emission plus this non-isothermal sheath, you end up with a law that is like this. So you have one branch like this, then you bend back like this, and then you have the saturated regime here. So you have a range of electron temperature where you have actually 3 possible equilibrium for the sheath potential, basically. And in fact, indeed, when you do the power balance, and if you are in the appropriate regime of electron temperature, if you cross here, you find that this equilibrium is unstable, and those two equations here that I showed before are going to lead to relaxation oscillations like this, where you see this is an example of the emission, but you can also find that with the potential and temperature. So you have a sheath instability. With waveforms that are quite well predicted, this is modeling the unstable regime, which is the regime 2 here. Frequencies are not quite exactly the same, but we are currently continuing investigating. So this was my first example in all thrusters to see how sheath physics, which is useful in many of other applications, can be revisited to explain some phenomena that you observe in plasma thrusters. And I believe that what has been observed here should maybe be considered also in other situations of for example, in plasma etching or in high beams or in other plasma processing things. I will now take another vehicle, another example to show you that you can interest people that are not at all from the basic physics, plasma physics community into the game. And this is because thrusters may be appropriately operated with molecular gas propellant. In fact, it's been known for a while that you can and this I took those slides from another PhD of us, Florian Marmus, who presented last Tuesday. Molecular gases can, in fact, be divided into two categories, basically. Either you have a simple molecule, for example, a diatomic molecule that you can easily break, and then you're back to pretty much the atomic gas that you want to ionize and accelerate. Or you could be in a category where you want to make very big molecules that you could ionize once and accelerate, but for one ionization, you accelerate a lot of mass. In this first category here that we've been interested in our lab for a while, the best candidate seems to be iodine by far. Iodine is in fact very easy to dissociate. The energy of dissociation is very low, and you see that it's very close to xenon in the periodic table here. And therefore, when you look at the properties, in fact, if you compare to xenon, it's about the same. Xenon, which is by the way the noble gas that people use classically in thrusters. If you compare iodine to xenon, you find that the mass, the ionization potential is in fact even better than xenon. So mass, ionization potential are very much comparable. And in fact, a great advantage is that it's very cheap. It's solid state at room temperature and standard condition, and therefore it's very easy to make to compact that to do some tanks basically for thrusters. So you have almost all the advantages, except that maybe it's a corrosive gas. Like we are very used to those gases when you do plasma etching, for example. We are used to use chlorine or HDR or complexes like this that are corrosive. In space, it's not that obvious, but people can cope with this. So this is the only drawback. But apart from this, in fact, it's been shown to be a very promising propellant. for thrusters, and not only for advanced thrusters, but even in Hall thrusters or classical bladed thrusters. We came to be interested in iodine in our lab because, in fact, we were studying a thruster that was making negative ions and trying to make large negative ions by having a magnetic filter that will cool down the electron temperature, and then we will be able to generate an ion-ion plasma downstream of this magnetic filter, and then we would accelerate ions out of the pulse acceleration of ions out of this thruster. We call that this Pegasus thruster that we studied quite a lot. Actually, Annie Aniston was taking over this project for a long time. And but we got interested in iodine, and we studied iodine actually not even in the context of this thruster, but in the more general context of making a propellant for any thrusters, basically. And we discovered that iodine was not very much known as a gas, actually, although it was studied in the early 30s as a gas to produce negative ions and study electronegative plasma. But yet the literature is very short and weak on this, so we decided to study this. And I will just give you a few examples of what we did. And in doing this, for example, we got interested. We got interest from other scientists in our lab, like for example Jean-Paul Vout, who is maybe in the audience, who is not at all a fan of thrusters, but as soon as you put molecular gas and if you can do spectroscopy, then he runs back. So JP got interested, another researcher, Cyril Drake, got interested, and we started to look at the way to diagnose this. We did, for example, laser infrared absorption on one transition here, which is usually a forbidden transition here on the ground state, which is has a very weak cross section for absorption. So we had to do several paths across the discharge to get some signals, but we were able to get some signal. I'm not going to give you any details in this presentation, but just to give you a flavor. And by doing absorption, of course, what you could do is you can do, by integrating the profiles of those lines, if you have the appropriate cross section for absorption, you can get to the absolute density of the iodine atoms. And by monitoring the broadening of the line, you can even measure the iodine atom temperature. So we did, and we obtained results on this. We were able also to do broadband absorption spectroscopy on the I2 molecule this time. So we use a broadband lamp across the discharge with this very large spectrum here, and you go across the discharge and you can absorb light with a fairly large absorption this time. The problem being that with plasma you can pollute the window, and therefore we have to have those buffer windows here where you have boost angles, but this is a problem because it's regions where you can store some cold gas, basically. But anyway, we were able to do this. This is an example of the spectrum with absorption, before absorption, some of the light, and then after absorption, and you see there is a difference. This difference gives you an optical depth, and if you look at the cross-section from the optical depth, you can get the density. In fact, there is a lot of solidity here that I don't have time to discuss, but we found, for example, that the cross-section was not easily, you cannot easily use it in the full scale, but the appropriate scale to use it is in this region from 480 to 500 nanometers. And when you do this, you can monitor the I2 density by your absorption, and you use ideal gas law to verify this. And we found that there was a beautiful agreement comforting for 300K at room temperature, comforting us in the fact that we have a good diagnostic for I2. So if you're able to monitor I2, I atoms, and then there are other techniques maybe to explore the ions, then you can start really diagnose this iodine plasma quite deeply, and compare to modeling and to simulations that we also do in our lab. When you put plasma with iodine, we found some difficulties. Again, this is because you have gas heating, you have some gas that is going to localize in the window, so you're not sure exactly what you're measuring. So all these I atoms and I2 molecules, we did absorption, and therefore it's line integrated densities. So much more research it's just the beginning, basically. It's the beginning. If you compare to what has been done in oxygen or in chlorine, clearly we are in the beginning of the road and not at all at the end of the road. And that was my second example, and it leads me to the end of this talk, which was a little bit of teasing to tell you a few things. First, plasma processing for microelectronics and plasma thrusters, which are the two areas that I know about in doing research. They share many similarities, in fact. It's low pressure, very low pressure systems, low temperature plasmas. The interaction with surfaces, it's very important. And you may have fairly high energy involved, either ions or electrons. And I'm convinced that one day or another, people will use molecular gases as propellants. I'm almost convinced that resin will be one day or another a serious problem for thrusters. So it means that all the research that has been done in microelectronics will have to be done again with different gas, of course, but in this thruster area. Both types of plasmas are essential to industry. This is a very important point to me because, in fact, I think, again, doing research in something that works looks sometimes boring, but in fact, it's not. It's extremely important and extremely stimulating, in fact. You could not make any chips without plasma processing. You could not go anywhere in space without a plasma thruster. And even now, around Earth, every satellite will be equipped with thrusters, which means that the research that we do in plasma is extremely important. In fact, those are typically areas where you have no plan B, basically. There's no plan B, you need a plasma. And I think it's very exciting for us. Another thing that is I'm almost certain is that high-performance computer simulations would be useful for design and optimization of those complex devices. It could be in microelectronics. Our chairman, Shahid, is very well aware of this, by the way. But it's same for thrusters. But the complexity is so large that, in fact, you need a very, very serious verification and validation approach to make sure that your simulation are telling something that is reasonable, basically. And maybe the last bullet is a summary of everything, is that you need fundamental research. And with this, I would like to thank you for that. And I take any questions. I can't hear anything at the moment. I can't hear you, Shahid. I can't hear anything. Okay, that's getting embarrassing. Let me, I don't. Mark or Zoltan, can you hear me?
Having mic issues, so there are a number of questions.
Okay.
Greg Seven is asking that how big is the plasma potential in the channel, and doesn't this repel electrons a bit? Thanks for this interesting talk.
So Greg, I suspect you mean in the Hall effect thruster. So in the Hall effect thruster channel, the electron temperature can get up to nearly 20, sometimes even more EVs. The classical floating, it's a floating sheath because you have dielectric walls. The classical floating sheath theory would tell you 5T, it would mean maybe 100 volts. However, because of emission and because of this non-isothermal sheath feature, the potential that we observe is lower. It varies between 50 to 100 volts, but I'm talking about what I know from our simulations. As you may know, it's not easy at all to put any probes inside the Hall effect channel, Hall thruster channel, because the energy is so high that the probe melts. So I don't know how much it has been verified experimentally, but typically the order is about 50, 70 volts. Okay. Xenon looks simple, but in fact, it's not simple. I mean, it depends on how to speak to. I mean, if you speak to our colleagues from collisions, they believe that the xenon is already extremely complicated, and all the cross sections of xenon excitations, etc., are quite difficult to compile. But of course, iodine is even worse because you start with a molecule, you start with a molecular gas. You pretty much know what is the energy to dissociate this, so that should be okay. You know about the potential of ionization, but cross sections are far from being known. And for example, something that we faced with JP when we studied the chlorine system, all the vibrations, the vibrational states were extremely important. I don't know anything about vibration in iodine. Another thing, and this was a discussion that we had with Jon Gudbrandsen, what about the attachment, the dissociative attachment cross-section of iodine? Iodine was believed to be a very attaching gas, very electronegative, and when we did experiments with the magnetic filter in the Gaseous structure, we in fact indeed found that you could provide an ionized plasma quite easily by filtering the electrons. However, when we started to put quite a lot of power without magnetic field in our device, we exploded the molecule entirely, we believe. And therefore, even if the attachment cross-section is important on I2, since you dissociate the molecule, you end up with not a lot of negative ions. But we are not sure. All this we're not sure. The excitation, how you split the energy, all this is extremely complicated. In fact, it is gas heating, of course, is a very important issue in those systems. So I think, as I said at the end of my talk, for me, it's more the beginning of the road than the end of the road. Molecular gases, diatomic molecules, it's extremely challenging. Even when you speak about N2O2 that are extremely known, it's challenging. Cl2 that is a little bit more known, it's also challenging. So I2, we open a new book, basically. That's my vision.
Okay, thank you, Pascal. There are a number of additional questions, but in the interest of time, we will move to the next.
Sure. Thanks very much.
I think the questions will remain in the Q&A box. So hopefully you can interact with the...
Yeah, people can feel free to email me, by the way, if they want to discuss some specific questions, or there's no problem at all.
Sure. Thank you.